Hi, my name is Will Krozik, Scientific Services Manager at Chemical Computing Group. Today I'd like to demonstrate the fragment-based drug design tools that we have in Mo. In this example, we'll be exploring the Combinatorial Builder, which is a useful operation when we want to generate combinatorial libraries by placing energetically allowed alternatives simultaneously at several attachment points. So let's get started. So I'll just use the Open button to retrieve the file that we're going to be working on today from the sample mol directory. I'll go ahead, select that in the Open panel, hit OK, and I'm greeted with this Load PDB file panel, which allows me to select what data we're going to load into Mo. Here, I'll just accept the defaults by hitting OK, and we see our structure appear on screen, and we notice that the protein is coloured by its secondary structure, so beta sheets in yellow, helices in red, and turns shown in blue. Before we can start thinking about fragment-based drug design, the very first thing we need to do is prepare this model. It's a raw PDB file. Typically, it won't have any hydrogens or charges calculated. Perhaps there are also some missing loops. So we can address these issues and ensure we're working with a high-quality model using QuickPrep, the automated preparation wizard in Mo. The panel itself comprises three main sections. The first handling the preparation and cleanup of the structure. Second sets tethers and restraints. The third handles refinement. Again, I'm going to accept the defaults by clicking OK, and I get an indication that the calculation's been initiated and also a progress update at the top left of the main Mo window. Now, before I move on, I'd just like to take a moment to explain what's going on in the background. So the first preparation stage ensures that we've got a complete model. What we're doing here is adding in any missing hydrogens, charges, or side chains. If there are any missing loops in the model, up to 10 residues in length, they'll be grafted in. Protonate 3D optimizes the ionization states of the bound molecules and their side chains, and it also generates a hydrogen bonding network through the placement of polar hydrogens. By default, we'll tether our atoms that are close to the active site, and the reason that we do that is to ensure that we can retain the original geometries of those atoms as captured by crystallography. We don't want to lose those geometries to processes such as energy minimization. And likewise, we can fix any atoms that are 8 angstroms or further away from the ligand, and we can do that for reasons of computational efficiency. The final refinement stage of QuickPrep performs an energy minimization, which ensures that we don't have any clashes in the structure. So I see that the message has gone from the top left of the main Mo window. I'll just cancel this panel, and now that we've got a prepared model, we can get familiar with this complex, starting by a closer look of the interaction between ligand and receptor. So for that, I'll hit Site View, which isolates the ligand together with any residue within 4.5 angstroms. Next, I'll just open the System Manager and pin that to the main Mo window as a means to manage all of the data that we have in our system. From here, I can hide and show different atom sets, make selections. I can also render and generate surfaces. And right now, I'll use the rendering functions to hide the ribbon and colour our ligand a bright colour. So with that, we've adjusted the display as we'd like it. Perhaps what I'll do is just display our hydrogens on the ligand only. And next, what I'd like to do is get an idea of the size and the shape of the binding pocket. So for that, we can use a surface, and you can see some of the default surfaces available. I'm just going to use the receptor surface, which is coloured by its atom colour, predominantly grey for carbon, but blues and reds for the nitrogens and the oxygens. And here I can see that this group here is encroaching into the top of the pocket space. In this particular example, I'm going to want to make some substitutions at a couple of places. So for that reason, what I'm going to do is just select this methyl and delete it. And now our system is ready for scaffold replacement. So what we're going to do is use the Combinatorial Builder, which offers similar functionality to the Add Group to Ligand operation that we previously explored in another video. But in contrast, the Combinatorial Builder allows us to add multiple groups to our ligands simultaneously. In order to investigate where we might want to add these groups, I'm going to use the Ligand R-Vectors. So when I toggle that on, it'll annotate the ligand with these green arrows, and it shows me where on the ligand I can make a substitution around the size of a methyl, but without creating a steric clash. And I can see here we've got a couple of R-vectors indicating that we can make some substitutions in these regions. So next I'm going to go ahead and open up our Combinatorial Builder, and I find that within the Fragments submenu. So here we have the various operations that we have under the umbrella of Fragment-Based Drug Design. I'm going to be using the Combinatorial Builder, which opens the panel comprising 4 main sections. So the first allows us to define the system in terms of ligand and receptor. The second allows us to define the type of operation that we'd like to perform, and here you'll see the same options that we saw earlier within the compute menu. The third section of this panel allows me to add filters, be those descriptor filters or pharmacophores, and the final part of this panel allows for scoring and minimizing our structures. So I'll just move this panel to one side, and then I'll go ahead and set that up. So the panel is guiding me how to set up this run. It says use defined connections to associate R group libraries and specify the connection points by the selected atoms. So I'll start by selecting the atoms, and I'm going to select the 2 suggested attachment points. So I've selected those. They become selected in the main Mo window, shown by these pink spheres. It shows me in the combinatorial panel that we've got 2 connections, and I'll move down to the next part of this panel now, where we handle our filters. So I noticed that the Check Filters button is coloured red, and if I just hover my mouse, it tells me this button is coloured red if the ligands do not pass the descriptor filter. To understand why that might be the case, I can just click this button. I get extra information at the top left of the main Mo window telling me that our co-crystal ligand has a molecular weight of 514. But if I look at these filters, I can see that we've got a cutoff here for a molecular weight of 500. So what I'm going to do is just manually push that up to 600. As I move down the panel, what I'll do next is opt to minimize the generated structures within the receptor environment, and I'll also write a score to the output database as if we had docked them. So with that, I'll click search to initiate the calculation, and in the background Mo is now searching for linkers that grow our ligand not in one location but in 2 locations simultaneously, A1 and A2. So Mo is searching in the background a fragment linker database containing just over 40,000 structures, but we do have access to larger libraries if required. Now, I just want to take a moment to go back to the panel and just explain a point that I touched on earlier, and that's the idea of using the defined connections to associate R group libraries. So what this allows is that we can define different R group libraries for our 2 connection points. I can achieve this by clicking on the Define Connections within the panel itself, and here I can see that both A1 and A2 connections are actually pointing towards the same fragment database. But you can see that there's options here that we could assign a different database to connection A1 relative to a different connection, different database or linker database for connection A2. I'm not going to do that today, but that functionality does exist. So Mo is currently generating these novel structures, and it's also minimizing each of these newly generated structures within the receptor environment and scoring them as if they'd been docked. The results themselves are written to the database viewer. So this would be the format that we use to store database entries, and in this case, database results. It's also our launching point to various tools that we have in Mo. So for example, here I could jump into QSAR if I wanted to. The database viewer itself looks and feels much like an Excel spreadsheet, but if I just drag the mol field open, you'll see that it actually contains the 3D structure of our newly generated structures, together with some useful information. So here we can see that we've got the different R groups associated with each newly generated structure have been written out, together with some predicted properties, including that GBVI WSA score, which we can liken to affinity. It's a measure of how well that ligand is interacting with the receptor environment. And this would be an energy, so the more negative this number becomes, the better the interaction between the two. So here I can see that we're already generating quite a few results in terms of the progress bar. We've got a long way to go yet. So you can see you can generate quite large libraries using this technique. For that, perhaps if we're really generating large libraries, we might want to consider using the batch operation, which allows us to take the input parameters that we've defined here and write that in a format that is friendly for high performance computing, so we can send it directly to a queue or a cluster. But in this case, I'm just going to stop the search prematurely so that we can have a look at some of these results. So the first thing I'm going to want to do is organize our results according to the score. So within the database viewer itself, I can sort by any of these headers. So if I just go ahead and sort ascending, and it'll ask, are you sure you want to do that? I'm going to click yes, and what that does is reorganizes my database with the best results at the top. So the more negative scores are now at the top of the database, so I can prioritize my efforts on those. But beyond looking at the quantitative numbers, I can also use the database browser, which will allow me to investigate each one of these newly generated structures within the receptor environment. So this opens the Browse panel, which contains a 2D schematic of our newly generated ligand. I can also see it within the 3D environment, our newly generated structure in green relative to the original co-crystal structure in orange. And what I can do then is I can click through to investigate each one at a time. I'm just going to autoplay to cycle through those so that we can see the effect of the combinatorial builder and what it's done today in generating a combinatorial library by placing energetically allowed alternatives simultaneously at several attachment points. In today's example, we defined 2 attachment points, but we could add more if we wish. I'll just cancel that browse panel and bring back our original combinatorial builder and wrap up today's session where we use the combinatorial builder operation to grow the ligand at several attachment points. We also minimized our newly generated structures and scored them in the receptor environment as if they'd been docked. I hope you've learned a lot today. If you have any questions, please do reach out to me at support@chemcomp.com.